What you're seeing here is CO2 in parts per million. That's going up and down, and then obviously just a year. And you see that sawtooth pattern. And what that sawtooth pattern reflects is a seasonal signal. So in the summer, when the trees so right now in the spring, when the trees in the northern hemisphere put out their leaves, they soak up carbon dioxide for photosynthesis, and global CO2 levels actually decline at that point. And then in the fall, when the trees go dormant and lose their leaves, global CO2 levels go up again. So that's a sawtooth. But on top of that, as I am sure is quite obvious, we have that extremely obvious upward trend. So what this is showing us is that when people started measuring in the late 1950s, CO2 levels in the atmosphere were around 315 parts per million, and they are now up above 390 parts per million. So that is quite a significant increase. So figuring out how to measure CO2 was a big breakthrough, but it raised the obvious question of compared to what? What have CO2 levels been like over history? And this is a very important and interesting question, and scientists came up with a really ingenious way of answering it. And that was to drill a series of ice cores. So this is an ice coring station on the top of the Greenland ice sheet, which I visited about 10 years ago. It was called the North Greenland Ice Coring Project. It is on top of the Greenland ice sheet. This is we're at the very center of the Greenland ice sheet, which is 2 miles thick. So the ice at that point is 2 miles thick. When you're standing up there, you're standing on 10,000 feet of ice. What happens when you take an ice core is you just take this drill that you're seeing the drill there. It's just basically a long tube, and it has very sharp, edges at the bottom, and you stick it into the ice, and you turn it. You have a way of just twisting it around, and if you're lucky and everything goes well, it's actually quite technically demanding work. You pull up this cylinder of ice. It's about 3 feet long and about 6 inches in diameter. And you just keep doing that over and over and over again. And it's very boring, and it's very cold work, because as I mentioned, there's 10,000 feet of ice to get through. And when I got to North Grip, they were actually at the bottom, near the very bottom of the ice sheet. So they were pulling up these cores from nearly 10,000 feet. And it took an hour just for the drill to descend, and then it took an hour for the drill to get back up. And the reason that ice cores are so useful is because all an ice sheet is it's just layers of snow that have been laid down year after year after year after year. And then they've been compressed, and so their crystal structure changes, but all they are these accumulated layers of snow. So in that snow, you get, on the one hand, by analyzing the isotopic composition of every layer, you get a temperature signal, what temperature it was like when that layer of snow fell. And you also get, even more astonishing really, you get these little bubbles of trapped air. They're actual bits of an ancient atmosphere. So if you extract the temperature data, and then you also actually extract this air, and you can analyze it, and you can tell what the atmosphere was like thousands and thousands of years ago. So in Greenland, you can go back about 100,000 years, so roughly to the beginning of the last ice age. But when you go to Antarctica, which I sadly have never been to myself, some of you probably have been, you can go even farther back. You can go back many hundreds of thousands of years. So what we're seeing here are the results of a very, very famous, if such a thing exists, a very famous ice core that was drilled at a place called Vostok in Antarctica. You may have heard recently that the Russians were going to drill into a lake, Lake Vostok, that had not had contact with the air for many millions of years, and they're doing that at the bottom of this core that they drilled over the course of the 1990s with American and French help. And what you're seeing here in red is the temperature data, okay? And in blue, those are CO2 concentrations in the atmosphere. So you see how we get that interesting cyclical pattern, and the two move not exactly in tandem, but pretty close. And you see that the way they've moved up and down, that corresponds to the ice ages. So we are looking at 4 glacial cycles there. 4 times, okay, when the glaciers moved into the northern part of the US, northern Europe, all around the northern hemisphere, and then retreated again. And you will also see, and this is a key point that I'd like to emphasize, that CO2 levels have not been above 300 parts per million for that entire 400,000 year period.